Hey everybody, I'm so glad to be back. Second time, yes. Second chapter, and I want to promise you one thing. I'm going to give the best talk I can, but you'll remember the Q&A more than the talk because I brought some friends. So I look forward to the Q&A. Also, by the way, last time I enjoyed the Q&A better, more than my own talk. What I want to talk about is the next chapter. In the story I talked to you about, and just for those of you who were not here the last time, I wanted to just kind of go back to what I talked to you about. Of course, what I talked to you about is Voyager. And I talked to you about a mission where every bit is sacred, where every bit told us the stories about the outer solar system and the boundary region of our solar system to the galaxy. And I wanted to tell you it's a really great time to give that talk because November 15, something really important happens. Does anybody already know? November 15, Voyager is 1 light day away from Earth. It's the first object to ever do that, in which we're in contact, a human-built object. And of course, it's the mission of my lifetime. So kind of for me, it stretches my mind. It's 1 light day. Of course, the frustrating part is the next star is a few years away. So it's like it's going to take a while to get there. But the point is, what an amazing feat. So kind of if you look at Voyager, kind of zooming out, it of course went by all of our planets, the outer most planets, and it's on the outside there where it's hanging out. It's on the outside of that bubble that's inflated with solar material, and it's in the outside of that in the galaxy, hanging out in the galaxy, and making measurements right now with only 2 instruments still turned on because the others are frankly out of power. It's close to freezing. It's so cold out there because the sun is really far away and there's no star in sight, and it's just being kept alive with its little battery that, of course, is decaying with the decay constant of plutonium. So the compute capabilities we talked to you about are these. Bit rate is a little bit less than 120 bits per second. And frankly, only with the biggest antennas at that level, 70 meter. So that's what I talked about. I talked to you about Hubble also with the launch in 1990. And of course, it's a spacecraft. Frankly, Lee, who's going to come up here in a minute, worked on Hubble and actually was the guy who helped fix it. You may remember that it was a little bit short-sighted. And because of a mistake in the mirror, and our friend Claude Nicollier, which I don't know whether Lee met, but no, Claude Nicollier was the famous Swiss handyman in space. Very much liked, went and fixed it. Its capabilities are about here. So we went from 100 or so bits to close to a megabit per second with 400 terabits of data. The reason I'm telling you that is because I'm going to now talk about a spacecraft that is taking that forward. Before I do so, I just want to remind you of the amazing things that Hubble saw. And I kind of want to talk to you about 2 things. The first one is it showed us that the universe is full of galaxies. Webb showed us a lot more, deeper, but this is a very small spot near Polaris. So if you look up it there, a dark spot that where Hubble for a week long focused its attention, and to everybody's surprise, I believe, saw in a large number of galaxies. Kind of the way I talk about it usually is behind a grain of sand stretched out on an arm, or of the order 6,000 to 10,000 galaxies. Each one of them, by the way, 100 billion stars or so. Each one of those stars, at least 1 planet. That will mess with your mind. So this is a picture of Hubble of supernova 1006. You see, it's like a band, like somebody, kind of a band fell off a clothing, piece of clothing. It's hanging out in space. And you say, why is it supernova 1006? By the way, if you looked at that place in X-rays, it looks like a bubble, like a bubble that's inflated. And see the band, you see the little square there? That's where Hubble took the image. The reason I want to talk to you about that is because this galaxy is very much tied to Switzerland in a way I learned last year. I did not know that a year ago. Because it's supernova 1006. So why is it 1006? Because we know exactly when it fired. Why do we know? In this library in St. Gallen, there's a book, a little book that was filled out by the monk who was in charge of taking notes. And in that book, in April 1006, he wrote down, there's a new star. He said what a star is, and he said for 4 months, the star became brighter and fainter, and all of a sudden it disappeared. By the way, he's not the only one. There's 3 more kind of documents like that in the Asian kind of continent, in China and similar. And so we know for a fact where this supernova, this exploding star came from, of which Hubble took a picture. So that's kind of a prelude of Hubble. What I want to talk to you about is in this new chapter of exploring space is the Roman Space Telescope, which will launch. Frankly, currently it's set to launch on August 30, 2026. So I don't have time then because I'm at that launch. I'm sure other people in the room will also be at that launch. Hubble is very different than the James Webb Space Telescope. Remember, I showed you the James Webb, how it's folding out, 6.5 meter mirror. The Hubble, the Roman, if you look at it, the mirror is actually very similar to the Hubble Space Telescope, just 2.5 meters roughly. This, right? So I could just like go lie down on the mirror. It's too clean, so I wouldn't want to do that. But you get the point. It's a mirror that is as big as Hubble. However, it has a sensor and kind of a focusing plane which is much, much bigger. So during a given time where Hubble is looking at the sky in that little square, Roman is looking at an environment that's much, much bigger, all at the same time. So it's collecting data from all these places on individual chips that are lined up in that focusing plane to cover that entire area, kind of in a way that it's of the order 100 times faster than Hubble. So basically, what's happening is even though we use the same mirror, we use technology that totally amp up the data in a way that's absolutely unexpected, has never been done in another telescope. And so for me, that telescope is something I wanted to talk to you about, just because it's such a transformation on the data side. You could say, why would I want to do that? So I showed you 2 pictures of Hubble. I showed you how precise and beautiful the images are that are being seen with Hubble, from ultraviolet through the visible into the infrared. This one is mostly infrared, but it's really focused on not just, if you look at the sky, a stamp in the sky, or, take a grain of sand kind of covered by, Hubble is a little bit bigger than a grain of sand, but, the field of view, a little bit bigger. But the point is, you just imagine kind of a thumb against the sky, and Hubble is observing it. Now, the one thing Hubble has, it's actually going around the Earth. So every once in a while, you look at it, and then you disappear. You look, you need to look at somewhere else. You come back, look at the same spot again. Roman is going to go hang out 1.5 million kilometers towards the kind of away from the sun, from the Earth. So back there is what they call a Lagrangian point. It's a place where you put something and it largely stays there. That's what I told you last year, where the James Webb Space Telescope is also in that region. We need to correct a little bit the orbits, but the point is it's there. So what we can do is we gain speed because of the fact that it's a much larger field of view, instantaneous field of view, but also because we don't have to constantly look away. We can just sit and stare because we're back there away from the Earth and just hanging out. So why would I want to look at the universe so broadly? Instead of looking deeply in one place, I want to look many different places. It's because there are questions in astrophysics that are not resolved. Everything that I've showed you with the Hubble, everything you've seen with your own eyes, including with Chandra, the little supernova, everything is visible matter. That makes up 5% of the total energy in the universe. Dark matter, by the way, the first guy who figured out that there's dark matter that is needed is this guy called Zwicky, another Swiss guy who was a Caltech. By the way, terrible human being, apparently. It's horrible to work with. He's an amazing scientist who, as one of many, Rubin later came and basically gave it the name, but he figured out that rotational curves in galaxies kind of implied that there's more mass there than we can see. Dark matter of the order is 27% of the total energy. And then the rest is dark energy, which is basically has an impact on the universe that it actually increases the speed at which the universe expands. Dark energy is probably a property of space. It's probably not something in it, but a property of space itself that basically is generated as the universe expands. What Roman is going after is everything that's called dark matter, dark energy, and it's doing that by imaging the sky at large amounts of data, large amounts of angular area. So basically what Roman is going to do is, by opening the eyes so broadly, is going to look at 100 billion stars, a large fraction of the stars in our own galaxy, 80,000 supernova explosions of the type I just showed you, like the monk in St. Gallen. By the way, it's really rare that you see a supernova with your own eye. In my lifetime, there was one so far that I remember. And then what we also see is many of the other objects, some of them are just mysterious, like black holes that are at the center of galaxies, sometimes also floating around, billions of them. And then exoplanets, planets around other stars that also will be observed by a variety of ways. The most important part of this chart, though, is 1.37 terabytes per day. So in one day, remember 400 for 33 years or so for Hubble, 1.3 of those in one single day.
We have a standard model that is exquisite at describing the properties of the universe that we live in. But there are hints of a problem with that model. Roman will tell us if our model is wrong.
You good? We're ready.
And what's spectacular about Roman is Roman will be able to tell us if we were wrong and put us on the path to figuring out what's right.
Starting run.
This time, a year from today, we're going to have a different understanding of the universe than we have right now because of the observations from the Nancy Grace Jones Space Telescope.
All reports test complete.
Yeah. We're super excited to go launch it. And by the way, I'm just excited that you're going to meet one of the leaders of that telescope who's sitting right here. And she just moved to Zurich as well as the James Webb Space Telescope leader who's also sitting here. So basically the compute capability of Roman, remember we're always talking about data, are much better than any of the other things I've talked to you about with enormous amount of data. In 9 months, it will overtake the Hubble. Which will at that point be basically operational for 36 years. And the total data over 5 years is 20 petabytes. So basically what we have now, and everything I told you before was not impressive. when you look at data like at the Earth or so, all of a sudden, what we really have done is bringing big data into space astrophysics. And frankly, we have done that in multiple stages. The first one is, I already told you the last time, that in 2018, all Hubble and now also Webb data are basically put into the cloud, which at this moment in time are roughly 200 terabytes of data that are already available. By the way, they're public, so you can go play around with it if you want to. Find interesting things people haven't figured out. I always tell this to children. I encourage them because I have stories of a student coming in as an intern at Goddard, where our two colleagues used to work. Actually, there's another one now that wasn't even at NASA, played around with data and immediately found exoplanets. So planets that were not discovered yet around other stars, just by hacking around in the data. So you can do it. They're there. Let's go find them. So basically, Roman is entirely dependent on that. And frankly, with tools that are not kind of scaling like we used to. I always said kind of the way we discover astrophysics is one grad student at a time. Like, we give a grad student a problem and they can do whatever a smart person can do and move science forward. That's not the way it's going to be. Frankly, basically, even now, many of the most important analyses are about all data of a given type, not one single shot, which is what used to dominate science something like 15 years ago. So basically what you see as we're looking at the universe, these very important questions about how the universe works, the dark matter, the dark energy, but also how galaxies work, how they evolve. The way that's done is looking at cloud computing, at all data, at agentic type of solutions that are kind of coming and taking over some of the things that we're doing. Of course, I would be very remiss if I didn't remind you, and of course you already had an amazing talk today about weather forecasts and data that relate to that, that focus on our own planet. And I just want to tell you that I think these solutions and kind of artificial intelligence type of solutions are really making an important impact as we go forward also in that. See, what we used to do, and of course my colleagues can confirm, is we used to always match the data we're collecting with what we can bring to Earth. Yeah, we compressed a little bit, but largely speaking, whatever came in the front, we were playing back to Earth. And yeah, we had a storage, but we sized it such that the storage didn't just go to infinity. So what we can do with edge computing is two things. First, we can compress the data smartly, and we can make decisions near real time or real time. So imagine there's a number of spacecraft flying around the Earth, and a spacecraft comes and says, hey, there's a fire here in Greece on this island. We saw the first smoke. That's what I see. The agent on top of that spacecraft, the code that was used to train that, can tell the next spacecraft coming behind, hey, watch out there, go check, put your attention to that spot and measure what's happening there. So those are solutions that are happening in so many of the areas. And then, of course, there are specific chips that were actually developed for this that are, frankly, a number of them are in space as we speak. And basically, the biggest question is, how do we keep them cool? I don't know how many of you have experience with these chips, but, they make excess energy. And in space, of course, we can radiate to the dark sky, but the overall kind of performance of the chips is still limited by whether we can get the energy out. That's why kind of cooling systems are really, really critical that are there. So that's what's happening here around Earth. And this is a spacecraft, by the way, a spacecraft we're working with in our GeoLab, a spacecraft that basically has 30-meter resolution. And it doesn't just take an image in 4 colors like most Earth imagers, or in 7 colors like Landsat. It takes images in 424 colors. And so that's a massive amount of data. It does so with 30-meter resolution over a swath of 18 kilometers. So if I fly over a tree, not only do I see it's a tree, you can figure out what tree it is, but you can also figure out whether the tree is healthy. Because if a tree decides I'm under pressure, for example, I don't have enough water, it will actually stop its photosynthesis. I can see that right away using this. And so, frankly, we're using these data for a number of applications related to farming in Switzerland and elsewhere, precision farming, but also for many applications such as the stability of mountains in the context of landslides, where we use other technologies as well. But these are examples. This can only work, this kind of thing, because an avalanche of data is coming in the front, much more so than can be played down. And that avalanche of data, of course, requires that there's, if you want, cloud compute right up there in the chip. So remember, we did the first one of these. This is a commercial image by Planet Labs, but the first one of these in the civil space we did on the space station. I remember we immediately found methane that was escaping many wells. We saw them from without trying to find them. They stand out like a sore thumb around the Middle East and other places where oil is being dug. And so the team at NASA started to get on the phone and tell everybody, hey, you're leaking methane. By the way, leaking methane is bad for all of us because it's a greenhouse gas, but it's also bad for them because methane that leaks out of their systems, they can't sell. So it's just stupid. So go fix it. And so, of course, what's happening now, Planet did these solutions, actually created that out of the technology we did at NASA, created a whole fleet that are flying now in space. And frankly, many more are being built. By the way, the one thing, just as a number, the one mission I built at NASA with, I was responsible for at NASA, JPL built it, was 140 million. Planet can do theirs for 10 to 15 million. So, of course, they're not inventing it for the first time, but they're taking over technology and mass produce them. So that's why this kind of technology, this kind of measurement is going forward. The next chapter, and I'm not going to come back next year, but the next chapter, of course, what happened this year, and I thought I'll mention it, is kind of one step above, which is really that space-based data centers are being discussed, which is one level up from everything I just told you. The reason for that, of course, has to do at least with three motivations. The first one is data centers are increasingly hard to build on Earth for good reasons. There's, they take a lot of energy. Depending on how you build them, they take a lot of water. And so basically, if you look at the cost, the energy cost is really important to operate a data center. That's number one. The second one is people like Swiss companies or governments, they want the data not in systems where they're leaky, where other countries or other operators can take away. If I have a spacecraft with my name on it and the only person that can get the data in and out of the spacecraft is me, the data are as safe as they can possibly be. I don't know whether you saw that Axiom Space just opened. Just announced that they're opening a place in Lucerne. That's one of the systems they're going to go after, just for that reason in part. And then the third one has to do with the fact that a lot of what's going on in the space, some of it we don't really want to talk about or kind of scary, and that is that a lot of kind of what used to be on the Earth, kind of the war type of scenarios that used to be on our Earth are happening in space also, and fast decisions need to be made. That's the other reason you put this stuff up. But if you go at data centers, if we all expect that the cost of energy is going to go slightly up and the cost of launch is going slightly down, roughly in 4 years, we're crossing over. And so this is the cheaper way to do it. So what I tried to show you is the transition from Voyager last year, the transition from James Webb last year, and Hubble in the middle to this kind of new computational capability of bringing astrophysics observatories into space using the technology you all work on And what I also wanted to show you is that the very same technologies are also transforming how we're looking at our own planet, the most beautiful planet we've ever seen here on Earth. And so with that, what I'd like to do is stop and look forward to the Q&A. That's why I came. Thank you.
Thank you. Thank you so much. That was my slide. But now I first like to introduce to you the two people Thomas mentioned before. We have the honor to have here on stage Jody Dawson and Lee Feynman, formerly NASA system engineers, and now joining us in Switzerland and on the ETH projects here in Switzerland. Please have a round of applause. Guys, first question before we come back to the topics. How do you like Switzerland? Did you come with prejudice and did something came true?
Do you want to answer that or should I answer? Well, it's absolutely beautiful. I made the right decision, and for me, it was a change I wanted to make, but I can't say more than enough good things.
Yeah, I would pretty much echo that. I've only been here 5 weeks, but so far it's wonderful. And I'm really enjoying living in Europe and experiencing the mountains. Yeah.
Perfect. Thank you so much. Spread the word. We are. Oh, no, not extra material. So, as in a tradition of Cloud Native Zurich, Thomas opens up every event with a few numbers. I also brought some numbers. I don't know if you recognize them. Good.
I don't.
I read it in NZZ am Sonntag that these are the key numbers of the moon mission that is going to take place in 2029 starting. There will be 29 missions to the moon from the US. They want to deposit 4 tons of material on the moon, experience or research 22,000 kilometers of ice on the North Pole. South Pole? No, I don't. South Pole.
South Pole.
I knew you know it. And they also have like that energy stations that produce 100 kilos of energy per station. So I read that article like 3 times and I came up with like a million questions. But I thought I will ask you guys, what do we have to question ourselves at this point of time with these numbers?
Go for it, Lee.
So is the question really like, what do we need to be concerned about, or what is exciting about these numbers? Or because I think it is both. It's ambitious. But that's what we have to be to get to those numbers. I think what you're clearly seeing with these numbers is how the game is changing a little bit. And yes, we're going back to the moon, but it's becoming more of an economy on the moon, right? And with that, you think of infrastructure. I mean, I'm sure you guys are already thinking of how we're going to work with data. And yeah, I mean, it's ambitious, but I think it's absolutely exciting.
Yeah, and I'll just add, I think, one of the things I didn't quite hear you mention, but I think was implied is there's also this idea of putting nuclear power on the moon. I mean, power is a really big deal when you have these 14-day dark patches on the moon. We saw that on some of the lunar landers, where there's only a limited amount of sunlight. So I think that would be game-changing if we could do that. I think, if you had unlimited power, now you can really imagine a community on there. So that was one that got me excited. I think that might be one of the most ambitious and hardest, but yeah.
Oh, I agree.
Survive the night.
I agree. And frankly, the number of landers we've produced so far are 2 per year. So we need to 10x that. I don't know whether you've ever managed to 10x a production rate. That's really hard. So each one of those numbers is really hard. I don't know, 29 is hard. Especially, I don't know whether you saw like 2 or 3 weeks ago, a rocket exploded. That was really important for that transport. So 29 just got a little bit more ambitious. But I agree. I actually prefer really ambitious goals and being a little bit later than the ambitious ones, than goals that are easy.
You know, a number you didn't put was 5. You know what 5 is? 5 is 5% of the U.S. GDP went to landing on the moon.
It was 10.
It was 10%? Okay, I remembered 5%. But my point is that we're trying to do this for a lot less money. And we've learned a lot, but the question is, can we take what we've learned and do it for so much less money? And that's the hard part.
That's why I wanted you to raise the questions, because mine would be mainly concerned, but it's very personal. Like destructing the moon to make a living out of it, it sounds weird to me, but that's personal. So you raised some good questions there. Thank you so much. So I will delete the numbers and go back to the conversation. It's just for decoration, that you look good for the pictures. Yeah, we had a lot of talk before this event, and I think one thing that stuck with us was the topic of supercomputing. You mentioned it. There is a big chance in Switzerland to use it, to have it here. We also had a talk today about this topic. It's an advantage for Switzerland right now. Is it remaining? Is it in danger? Is Switzerland going forward with it? How are we in terms of supercomputing and using our data right now?
Look, I mean, I think there's 2 or 3 things that are going on at the same time. The first one is that the speed at which these resources are going up worldwide is staggering. I mean, you look at the investments on an annual basis, just look at it in China, look at it in the US, that the investments are just absolutely staggering. I mean, we're in not just in the billions, we're in, I mean, frankly, on 10-year timescale in the trillions, right? Kind of, and pretty quickly. And so basically that's what's going on. Many people see it as a competitive edge. I think what's also happening in parallel is that Europe has struggled with the evolution that is going on. So Europe is, even though many of the top leaders are frankly from Europe, in agentic AI and so forth, many of the top leaders, I always, the guy in charge of infrastructure of Google is a Swiss guy. Holzler is his name, from Basel, right? So many of the top leaders are from Europe. They're generally speaking not kind of thriving here, because I think what Europe is doing, and it's not wrong, is how you're implying, is kind of saying, look, there's some downsides to this we need to think about. And I think to a certain extent, that's the issue there, is that everybody knows there's downsides. The question is, how much do we need to know about the technology before we regulate? That's really where the difference is. And then the third piece is Switzerland in it. I really believe that Switzerland, because of its smallness, both its wealth, but its agility, can really carve out its own place. And so the question is, so I think the capabilities that we have, the Alps computer that you heard about today, frankly, you'd be hard pressed to find another kind of educational research organization that has that. I mean, MIT doesn't. I mean, your alma mater, right? I mean, they're building it, but they're not I'm not trying to be negative. It's really good. It's really good. It's not as good as OpenAI. It's not as good as some of the pharmaceutical investments, but it's really good. So the question just really is, how do we actually get the talent and technology developed for this world in which complicated discussions need to happen? They have to happen. We should not be blind to the challenges, but in a place where there's discussions being made right now about many things of the future, and Europe is just not at the table. So that's what worries me.
Thank you so much. I think one of the things that brought science always a leap forward was open discussion without politics, without geographic borders. Now we're in a place where open data is on the table, but it's in danger because of the geopolitical situation. And it also might not make sense for everyone to be in open science and open data models, but you would benefit out of it. So what are your thoughts on how using supercomputers, being in Switzerland, but still rely on the global togetherness in science?
I'm a huge proponent of global efforts, especially with the togetherness. I think Roman that Dr. Z talked about is a good example of that. That you have such a general observer, guest investigator approach to the science. We have to have the science available. Actually, we have a requirement for, well, I say we, but that used to be me, 48 hours. It has to be, in the SOC, the Science Operations Center, and it's getting it out the door quickly, available for people to look at. So I think the global aspect, especially of the Roman mission, is super important. Fully supportive of that.
Yeah, I'll say when I was working on the Webb telescope, there was a senator in Maryland who was very important to getting the funding year after year. Her name was Barbara Mikulski. And she was quoted as saying that great countries don't just build a James Webb Space Telescope, but they make the data available to the world. And I thought that was a really good way to think about, the things that are inspirational. And one of the things that really attracted me to coming to, Switzerland and to working on this, I'm working on a project that's searching for life. It's called the Large Interferometer for Exoplanets. And one of the things that really attracted to me to it is the whole philosophy of this mission is that this mission is really to serve all of humanity and to make the data available to everyone immediately that we get. We're going to be searching Earth-like planets around sun-like stars, looking at their atmospheres. And so, to me, I think this is something that we're getting back to your earlier point about Switzerland. I think this is a really sweet spot for Switzerland, is being a neutral country and being a technological leader. It's going to attract people who don't want to be part of the polarized world, but they want to be part of a future world that's a better world. And I think open data, what you're talking about, is exactly that sort of theme. So, yeah.
We just want to do good science and lots of it.
Yeah.
That's great. Thank you for mentioning it. I was supposed to raise the topic. Can I ask you something personal?
Sure.
How do you imagine the life out there? What is the picture you have in your head? Because I don't assume it's like the green.
The universe is huge, right? So I imagine there is life that is sort of biological, kind of like humans, but the life that we're going to be able to find with our telescopes is very unlikely to be that life. Will be, what I think is most likely that we could find is something very simple like bacteria or something like that. But the universe is so huge. I mean, on average, there's a planet around every star, and there's so many stars in the universe. So I'm sure it's out there, but it could be hard to find.
It will be hard to find, yes. But we all agree on there will be something, right? Yeah. We talk a lot about tech here, and I also had the round of video interviews. What do you like about that day? What do you think is happening these years? And one topic that was always raised by everyone was Gen AI and agentic AI will be a huge topic in the future. I think, and I assume that it is going to be a topic for you guys here on Earth, but also in space. How can we imagine that? What is happening?
I honestly, I personally think it's the way of the future. I think there's a lot of benefit, especially with autonomous mission operations, things like that. But it's all in how you employ it and implement it, and through a very rigorous, verifiable, step-by-step approach, instead of just having a pick your favorite AI bot, design me this mission. It requires a systematic approach. And I think it's a risk balance, but I personally think it's the way of the future, honestly.
Yeah, I think for space, I think it's the combination of robotics and agentic AI that's going to be so powerful. From servicing to we're already, deciding what to do with Perseverance on Mars from, AI. And maybe on the ground, a really interesting question is how is it going to be used in science? And I think that could be really transformative. And it's already done some really transformative things in some fields, not as much in astrophysics yet, but I think it's coming.
Yeah, I really think we're just at the beginning. And what we're also realizing that we're bad at estimating how fast it's coming. So last year, every once in a while, I go into tunnels. So I spend 40 hours on a topic, just reading everything I can learn, every podcast. So I was interested in math with AI. How long until AI can figure out new laws of math and kind of do proofs of math. Last year, the consensus was it takes 10 years. It's just the first publication just came out. So it was a factor of 10 off. And, it's a really interesting conjecture that was done. And the guy who did it is not a really deep and very experienced mathematician. And he did it on ChatGPT, right? And so he basically, so far, professional mathematicians have poked at it, and it's looking positive. So kind of, for me, it's an anecdote, it's not data. Kind of none of us know. What's really important, I believe, is I think what you're all implying is that there's certain potential. We need to learn about it. Kind of, it's a huge opportunity. I'm gonna say that to people also starting in their careers. You like when something like that happens at the beginning of your career, because it's almost like a poker game. Everybody gets new cards. Whatever happened in the past, kind of, it's the previous deck. Now you get a new chance. And so now the question is, who learns fastest? It doesn't matter where you sit, who learns fastest. But I think what Jody is saying is also true. There's also some really stupid things you could do with it, waste a lot of money or worse. And so basically you want to make sure that you kind of train. Good scientists are not just people who are great at discovering things, they're also great at understanding what it means in a broader context. And so both things should be trained. And I think Europe is particularly good at the latter.
So I don't want to take the stage on my own, and I think you already had a bit of time to prepare yourselves. Is there any good question? No. Is there any question? Oh, look at me. There are coming up a few hands. We have the mic there. I think, we can start here. Yeah. Thank you.
Thanks for the presentation. I have a question now. Space, belongs to all the humans, right? And what is the contention between the earthbound astronomy that is now increasingly affected by all of the pollution in the sky? For example, Starlink cost a lot. You say data centers in space. How is this is there a fight? And how is it, who gets priority, the earthbound telescopes or space?
But I'll tell you one thing that's really interesting is it's not just the earthbound telescopes. Even telescopes in low Earth orbit. I was just reading about SphereX, which launched in about a year ago. They're getting Starlink, smears in their data as well. So it's really anything in low Earth orbit or the ground, and it's at the point now. I mean, in Hubble images, where it's almost, it's commonplace to get these things. At the same time, I have to say, while they don't look nice, I still think they're pretty easy to remove from the data. So I think there'll have to be a lot more of it, and there will be a lot more of it. That's the risk before it really prevents scientists from doing, fortunately for Roman and Webb, they're so far away at the L2 Lagrange point, which you talked about, that they won't have this problem. And maybe that's what we need to do. We need to keep setting telescopes to the L2 Lagrange point.
I think to a certain extent, we grew up with dark skies. I mean, in Heiligenschwendi, I don't know where you guys grew up, but where I grew up, it was dark. And I know that I saw some technology flying by as a kid, but very little. That's over. I mean, so we're seeing a lot of it. So who regulates that, right? So the way what goes to space is regulated by each country with common rules. So there's actually no law that says that astronomy observations should be prioritized. Now, I want to tell you that SpaceX and other missions, including Amazon and so forth, have actually done roundtables with astronomers. I helped set up a number of these things, and they have changed their design to make them less bright, their spacecraft. So it's not, so they have, the designs are really different than they were at the beginning to help astronomy. And it is true for many of the applications, it's you can solve it. And nonetheless, I think I have a bad feeling in my stomach about your question, because I think overall the reality is that the sky will be less dark because of things that we're doing here, but also less clear because of things we're shooting up there. And there's a number of other questions I could add. I'll add one. So basically, each day, something like 50 metric tons of natural material is falling onto the Earth. That's just the leftover of the accretion, like dust, meteorites, and so forth. They're falling onto the Earth. In 5 years, we're crossing over. There's more stuff falling back to the Earth that we launched than what nature is. And so basically, in 5 years or so, we're crossing over. Now you say, well, is it not the same materials? Like, absolutely not. There's basically no aluminum in asteroids. And we're mostly dropping aluminum into the upper atmosphere. Will that do something? Well, initial studies say yes. So I'm not trying to worry you more, but there's a number of questions that belong to that. And I think it's really important that we think about them in a direct fashion. So frankly, we say, it would be great if we could build a spacecraft from atmosphere. And what is atmosphere? That's trees, right? Trees are condensed atmosphere, right? It's all the atoms come out of the atmosphere. So that's frankly what we're working on right now at ETH. We're launching something later this year to actually bring samples up to kind of see how the material behaves, things we can't test down here. All the other tests we've already done, and it looks positive, 30% cheaper than aluminum. So for me, it's these kind of questions that we want to go after and solve.
Hello, thank you. Regarding space and the rapid development of AI now, how do you see the Fermi's paradox? Do you know what I mean with Fermi's paradox? Why don't we see any life today? So, Fermi, maybe.
Fermi, yeah.
Yeah.
Yeah, you got it. What's your solution to the Fermi paradox?
Wow. I mean, I'm not an astrophysicist. I have my own opinions. I think, I mean, you guys all are familiar with Carl Sagan, right? He took, I think Neil deGrasse Tyson redid the series, and he compressed the life of the universe into a calendar year, and then humans fit in like, correct me, Dr. Z, like a nanosecond of New Year's Eve. And I think philosophically that we think we're so big and so important, but our lives are just so fleeting. And when you look at the technology development, super impressive from Voyager to Roman, right? And that's, just decades, right? It has only been maybe, 100 years since the first flight, 110-ish years since the first flight to the International Space Station kind of time frame, right? Like a lot can happen in 100 years, but that's still like that nanosecond in the cosmic calendar. So us being able to find all this life, we're just limited by our own capabilities, even our own eyes, and being able to detect all of the available photons in the universe. We're super limited.
Yeah, I actually agree. We've not been observable for a long time. If you look at it, the galaxy across is 150,000 years. We've been observable for like 100 years or so. Yeah. A little perhaps 200, right? So we've not been observed for a long time. So the real question is, are there shortcuts? If the physics we have right now, we don't know of any shortcuts. These wormholes that are, in the movie Interstellar and other things. Like, I wish that happened. I want to find one and go somewhere else. But like if there's no shortcuts, basically, frankly, there's very few that know that we're here. What's your view?
I think, like you were pointing out with Voyager, it's been traveling for that long and it's one light day. So I think, something traveling to us is incredibly difficult. And that's why, it's just statistically, it would be so far to get to. There would have to be some physics that, like you said, we don't understand. But light travels really fast. And, we've searched radio signatures for many years and haven't found anything. But those are, one specific way that life forms might implement it. I think, the project I'm working on, what we want to do is look at the atmospheres of these Earth-like planets. And I personally think that is probably the most promising thing to find some form of life. I just don't think I don't think we're going to find life that produces technosignatures within something that we can sense. So that's, I just think the universe is too big.
Yeah,
but they're out there.
You should know, when I was at the head of science at NASA, I started the technosignature observation program because I want to know. So we started, and we haven't found any. But we found a lot of other interesting things, which is why I did it. Even if we don't find this, we actually learn how to take huge channels of data and analyze it. And that's useful for many other things. So that's why I did it. So there's a number of really important insights. There are some candidates out there that look weird, but, we're poking at it, but, nobody has given us prime numbers back, right, like Carl Sagan's book, Contact, but that would be cool.
So one last question, and then we're running out of time.
Thanks for the amazing talk. I was wondering, you showed us a comparison between the fields of view of Hubble and Roman. And I was wondering, how did those two compare to James Webb?
You know what? I should have given you a different figure. So we have one of those that you can.
How does it compare?
Yeah.
So I will say Hubble and Webb are pretty comparable. Their total field size. I could go really into detail on this if you want, by the way, but they're pretty similar field size for the whole telescope, and then within the instruments themselves. Webb is a later generation, so they're a little bigger, but pretty close. Roman is way bigger.
Yeah, it's like people ask, is Roman launching and it's going to take over Webb? And it's like, no, they're two totally different telescopes. But if you remember that, we called it an upside down smile with the 18 detectors, sort of, the pattern of Roman. Webb is just like a little bigger than that Hubble square, but it's a square. That wide field, view that you'll get of the sky doing those slews is, to me, it's amazing. But sorry,
do you mind if
she worked on it a long time?
I did work on Webb
Do you
too.
mind if I just quickly tell you? I was so excited to bring those two. Just quickly tell you why. So James Webb. The major reason I slept is because of Lee and his colleague Mike, because they were the lead engineers of all of the James Webb Space Telescope. Humanity's biggest telescope is one of the two leaders who basically made it happen on the engineering side. All optics he did. And he's working now in Switzerland. And my encouragement was just find him and meet with him. He's literally want to know what's possible with astronomy. He would know. I don't know anybody better. And then Jody actually was one of the leaders of Roman. And she just joined to work on other missions. And, so you want to learn about that system and kind of multiple other things you've worked, go meet with them. They're all hanging around Zurich. Many of you are here. Go invite them, go hang out with them. I just think it's cool that we're kind of attracting this kind of talent and kind of all I'm just trying to say, that too, together with all the good chocolate and cheese, is a huge opportunity of Switzerland, and kind of we're only going to take advantage of the opportunity if we make something from it. So I just couldn't be more proud to see both of them on stage with me, and just my encouragement to you is make it work for you too.
Thank you so much.
Thank you.